Take a look at this motorcycle. It's claimed to be the world's fastest electric motorcycle, doing a 0-60 time in 0.8 seconds. We'll do an analysis on this. So let's take a look at our relationship or parameters in this one. Is it at rest? Certainly not. Is it constant velocity? No. It went from 0 to fast in a little bit of time. And therefore, because we don't have constant velocity, we know the forces are not balanced. To analyze this on the worksheet, let's go ahead and give it some of the parameters that we know about. The mass of the motorcycle and rider is 250 kilograms. The initial velocity, it started from rest, a standing start, so we know the initial velocity was 0. The final velocity, at least at the end of the 0.8 seconds, was 60 miles an hour, which I've converted into 28 meters per second, and the time listed at 0.8 seconds. Let's see if we can analyze this in terms of an interaction diagram, force diagram, position versus time graph, velocity versus time graph, and then we'll look at some acceleration and net force. Hey, so in this I know I have gravitational force to the ground, or sorry, to the earth, of a normal force to the earth, and there's certainly a frictional force here now. Okay, I did it before and after, it's moving along. Okay, let's go ahead and enclose this. I'm careful in my enclosure that I only wrap the object I'm interested in, the motorcycle, and then I cross through any of those interaction lines. First one, let's take a look at gravity. So I'll go put my interaction diagram over here. I have a force of gravity on the motorcycle from the earth, okay, and a force normal on the motorcycle from the ground. Okay, those are going to end up being balanced. And actually, how much are they? From our reading, we know the force of gravity is equal to mass times the acceleration due to gravity, which is 9.8. So in this case, we know the mass of our motorcycle with the rider is 250 kilograms times our acceleration due to gravity, 9.8 newtons per kilogram. How much is that? So it tells me my weight, or my force due to gravity, 2,450 newtons. We know it's balanced over here, so this must be 2,450 newtons as well. Okay, there's one other force we haven't accounted for, and that's the friction. And I certainly can see that friction is sending that thing forward. So the force of friction on the motorcycle from the ground. You can probably figure out how much that is. Let's take a look at another aspect of this problem. Hey, so let's take a look at our two graphs, our position versus time graph and our velocity versus time graph. One thing we know that just from our observation, that velocity started at rest, is going to be at 0, and it's certainly increased with time. Okay. The other is that this is accelerated motion, and it's accelerating in the same direction that we're moving. So we know position versus time is going to end up having a curve to it, like a parabola. Let's see if we can give these particular values. Okay. Hey, so for velocity, we know at this point our final velocity, 28 meters per second. That's converted 60 miles per hour at 0.8 seconds. We know that's 0.8 seconds. And that must be 28 meters per second. We see that velocity is increasing, so we end up having a curve upward for our position versus time graph. Okay, so now let's see if we can figure out what that value is. We certainly know that this is at 0.8 seconds, but what distance would it have traveled during that time? We know it's average velocity times time. Let's do the math. So my average velocity is my initial velocity 0 plus my final velocity 28 meters per second divided by 2 times time. Let's see what that works out to be. Whoops. My time is only 0.8 seconds. There. Times 0.8 seconds, and I get something like 11.2 meters is all it took to get to 60 miles an hour. Let's go ahead and answer our additional question. So what's the acceleration of the car? Okay, we know that that is our change in velocity over time. Our change in velocity was certainly the 28 meters per second. How much time to take? 0.8 seconds. Okay, let's see what that acceleration is. Okay, I get 35 meters per second. So the net force, I presented in both ways. Our A is equal to F over M, or more properly, F net divided by M, or the way we're talking about it this year is sum of forces divided by mass. We have acceleration, we have mass. Let's see if we can figure out what that sum of force is. So we get that goes to our sum of force is equal to mass times acceleration. We know the bike has a mass of 250 kilograms. The acceleration is 35 meters per second. So that net force is 8,750 newtons. When we use that, let's go on back to our force diagram. In our force diagram, we knew that there's 2,450 newtons down due to weight, 2,450 newtons up due to normal force. And now we see that there are 8,750 newtons, 8,750 newtons of unbalanced force, which is only due to this friction. We'll scroll through this just one more last time, just so you can see it. Hey, so again, we were taking a look at, this is certainly not at rest, not constant velocity, so we know our forces are not balanced. Listed our parameters, went from our interaction diagram to our force diagram, and then to our graphs. May have to go back and take a look at what these graphs are. Okay, hey, I guess I have to, like this. I know that this is 11.2 meters. That's as far as we got during our 0.8 seconds. We can match it up with grid work later on. Let's scroll on down. Hey, so we were able to figure out the acceleration by looking at the change of velocity from rest to 28 meters per second in the amount of time. In this case, it got 35 meters per second. Then let's take a look at what the net force is. Remember, the beauty of Newton's law is that acceleration is our rate of change of velocity, but it's also, where does it come from? Our net force is divided by our mass. Mass slows acceleration down, additional force speeds it up.